is the notes for section 9.7, logarithms to bases other than 10. If you haven't done so already, make sure you pause the video at this time, read the section first before continuing on with these notes. So when we were looking at 9.5 and we were talking about logs for the first time, we only looked at logs with bases of 10. Now what we want to do is say that, hey, we can extend that whole idea, everything that we've done with logs with base 10, which was just our common log, and we can extend it to all bases, or I shouldn't say all bases, but most bases. So to do that, we're going to define a log with a bunch of different bases, and that is the definition of the logarithm of a to the base b. Now, what does the base have to be? Well, it has to be a number that's greater than 0, and it also cannot be equal to 1. Okay? If that happens, we can say that x is the log of x, or excuse me, x is the log of a to the base b, or written like this. In logarithmic form, we write it as x equals log base b of a, or we can write it in exponential form, b to the x equals a. Okay? And then we have this, we have just a chart over here of different ones that we can write in exponential form and logarithmic form, and how that would work. So as you look at kind of the exponential form, the base is the number that goes down here, the exponent is what it's equal to, the log is equal to, and what 81, that would represent the log that we're taking. So that's your a value. Okay? So let's take a look at example 1 here. It says write the equation p equals 12 times 0.359 to the x in logarithmic form. Okay, well, to do that, the first thing I want to do is I want to get it so I just have some number raised to a power on the right side. So to begin with, the first thing I'm going to do is I'm going to divide both sides of this equation by 12. If I do that, I can say, and I'm going to put it right over here, p to the 12th, or excuse me, p over 12 is equal to 0.359 raised to the x power. Okay? So now think about it. This right here is your base. This is what we're going to take the log of. In other words, that's a. And this is what the log would be equal to. So I'm going to write it over here. The log with a base of 0.359 of the number p over 12 is equal to x. So let's take a look at example 2 here now, where we want to evaluate some logs with different bases. And to do that, we want to think about being able to move back and forth between logarithmic form and exponential form. So if I want to find the log base 2 of 16, really what I'm doing is saying the following. I'm saying 2 to what power is equal to 16. Well, think about that. 2 to what power is 16? Well, if I take 2 to the 4th power, I get 16, so x would have to be equal to 4. If I look at part B here, I'm really asking the question, 6 to what power is equal to the square root of 6? Well, you can think about the square root of 6, since that's a positive number, 6 to the x, that's the same as saying 6 to the 1/2. Well, therefore, their powers must be the same, therefore x would have to be 1/2. And finally, the last one, 3 to what power is equal to 1 over 81. Okay, so we want to think about that a little bit, and this might test your kind of arithmetic skills a little bit. You can think of that as being 3 to the x is equal to 81 to the negative 1st power. Now, 81 is the same as 3 to the 4th power. Therefore, I can say 3 to the x is equal to 3 to the 4th raised to the negative 1st. Therefore 3 to the x is equal to 3 to the negative fourth. Therefore x is equal to negative 4. That one was a little bit more work in terms of kind of doing that in your head, but it is very doable there. So let's look at the graph of the logarithmic functions and some properties of logarithmic functions. So when we looked at the log base 10 of x, we looked at its graph, and we saw its shape was something like this. We had a y-intercept of 1, etc. Well, the same thing really applies for any base. It's just that the degree in terms of how fast it's going to increase or decrease as x increases or decreases. So as I look at it, what I want to keep in mind is that it's always going to be the inverse of the function y equals 3 to the x, or y equals b to the x, I should say. So here, this is an example: y equals 3 to the x and y equals log base 3 of x. You'll notice that they're both reflection images over the line y equals x. I want to talk a little bit about their domain and range. Anytime we look at a new function, we want to be able to look at their domain and range. The domain, if I look at y equals b to the x, the exponential function, the domain we said was all real numbers, but we also talked about the fact that the range of values from that was always values that were greater than 0. Well, if y equals log base b of x is the inverse of it, you'll notice that the domain and range of those two are going to switch positions. So these two switch positions and these two switch positions. Now, if I think about properties of logarithmic functions, so we talked about their domain and range as being part of the properties of a logarithmic function, but we also know that all logarithmic functions will have an x-intercept of 1. Okay? And the reason for that is b to the 0 is going to be equal to 1 for all values of b that would work in a logarithmic function. We also know there's no y-intercept for a logarithmic function. If I think about the y-axis, which is x equals 0, remember, that's the asymptote of the graph. That's the line that the graph approaches but never touches. Remember, an asymptote is a line that a graph approaches but never touches. Same as when we looked at the log base 10 of x. Okay? And then finally, as we just talked about, that they are they're reflection images, both the exponential and the logarithmic, over the line y equals x. Okay? So let's take a look at example 3. We want to solve example 3 for a. So if I have the log base 81 of a is equal to 5/4. The first thing I'm going to do there, since I have nothing other than taking the log of a that's going on there, is I'm going to rewrite that thing in exponential form. So I'm going to say 81 raised to the 5/4 power is equal to a. The fourth root of 81, remember that the bottom number is the root, the top number is the power. The fourth root of 81 is 3, so really that's the same as saying 3 to the 5th power is equal to a. And then 3 to the 5th power, well, I know 3 to the 4th power is 81, and if I take 81 times 3, I get 243, so a is actually equal to 243. Now, I kind of illustrated how you could do that one in your head, and that's not a real easy one to do in your head. So we can go to our calculator and enter that as well. Finally, let's take a look at example 4 here. It says solve for z, and it says the log base z of 8 is equal to 3/4. So once again, I'm going to use the same idea. I'm going to say, well, if that's the case, I can write that in exponential form, which would be z raised to the 3/4 power is equal to 8. So now think about that. I'm asking myself the question, what number can I raise to the 3/4 power to get 8? Well, to undo raising something to the 3/4 power, I can raise it to the 4/3, because I know if I take 3/4 raised to the 4/3, that's the same as saying z to the 1st power, or just z. Well, if I raise that to the 4/3 power, I need to raise 8 to the 4/3 power as well. Okay? Now let's see if we can do that one in our head as well. 8 to the 4/3 power. Remember, the bottom number is the root, so I'm taking the third root of 8, which is 2. And then I'm raising that number to the 4th power. 2 to the 4th power is 16. Therefore, z would have to be equal to 16.